questions from anything? Let me check. There's some. I think the quizzes help much in preparation for the midterm since the questions are a bit too forward. Questions a bit too forward, which I can just find the answer from looking at the definition and the notes. I think I want to see more questions in like how to apply certain equations to find certain things. Okay, that's a great point. So we can do more formulas too in the quizzes. Will the final be cumulative? Yeah, the final will be cumulative, but it will probably be a little bit heavier on the new material just because I've already, in part because the new material is still actually a measure of the old material. They're quite related. Okay. So will there be a study guide? Yes, there will be a study guide. Oh, could I just ask, would you rather have the final on the last day of class, or would you rather have it during finals week so you have more time to prepare? And you can email me, message me privately. Okay, it's pretty split. Exactly half want it. Yeah, okay, so slightly more people want it in finals week. So we will, I think that just gives us enough time to prepare. Okay, yeah, now it's more than half, well, more than half. Okay, we can do that. I'm sorry there's probably about a third that wanted it on the last day of class. I can't do it one thing and its opposite at the same time. I think, so the finals week is scheduled. I will bring that, let me write that down. I'll find out what day and time it is. The final. Okay. So questions about yesterday or questions about anything else? Stephanie, I will find out what day it is and bring that tomorrow. Okay. So we're going to talk about hypothesis testing today. So hypothesis testing is something that we started actually yesterday when we would say, we think that the average student at UC Merced has a 3.0. We go out into the world and we take a sample of students and we say, what's your GPA? And then based on the average from that sample and the dispersion of that sample, we can calculate how likely we are to be right, that our guess that it's 3.0 is true or false. And we can also do that not just with averages, but we can do that with our regression coefficients. So we can find out whether our regression coefficients are what you'll hear this a lot, statistically significant. And just before we get into it, I want to give you kind of a clear example of what statistically significant really means when we're talking about a coefficient. So you might have data that look like this, okay? And I think especially if I have a point out this way and we drew a line through it, this would be, there'd be a coefficient on that would be something like, this would be a beta 1 equal to 1, okay? And then you can imagine a slightly different data set. And what I'm going to try to do is draw a relationship with the exact same slope. But that the data are much clearer. So here we would have our line going through that would be here, this slope would be also 1. But this beta is likely to be insignificant, which means that we're not sure that this slope is generated by a true uh, a true relationship between y and x that's different than 0. And why is that? Well, here the relationship is so tight that it's very clear that this is unlikely to be generated by something where there's not actually a relationship between x and y. But here you can see that the points, you could have almost as easily drawn a line that goes through the middle of them like this. That it's not being significant means that we're not totally sure that beta 1 couldn't also be 0. Okay. So I know that sounds weird, but we'll come to that in a couple of different ways, and hopefully it will kind of come in slowly. So how can we tell if an explanatory variable has an effect on an outcome that's meaningfully different than 0, that we're sure that there's not a 0 effect? How can we tell if multiple explanatory variables jointly have an effect on the outcome that is meaningfully different than 0? This is just our outline. We'll get right into it. We are specifically interested in testing hypotheses about usually sample means. So that's what we did yesterday, sample means, and regression coefficients. So regression coefficients are what we've been kind of thinking about this whole time, but sometimes to start with sample means and samples as much just kind of helps to apply the intuition for when we get to regressions. So luckily for us, both sample means and regression coefficients both have a normal distribution. So remember, if we went out into the sea and we kept sampling fish and weighing the fish, and we would plot how much the fish weigh in every sample, we'd say, okay, the average weight was 8 pounds. I don't even know what like a normal weight is for a fish. And then sometimes we get a 7, and sometimes we'll get an 8 again. Sometimes we'll get a 9. Sometimes we'll get a 10, but usually we'll get kind of things that are close to the middle. And then every once in a while, we'll get something far away. So each of these are when we re-sample the ocean and we just measure what the average is of the fish that we've sampled. What we'll eventually find is that if we get a large sample of means, we will find that the distribution of those sample means is normally distributed. And that's just that we call that the central limit theorem. And the central limit theorem says if we keep taking sample means, they will be normally distributed and they will be centered on the true mean, the true population mean. So the sample means are normally distributed around the true population mean according to the central limit theorem. And in a like fashion, regression coefficients, beta 1, are normally distributed around their true population values if the regression errors are normally distributed. And sometimes even when they're not normally distributed, actually. So that's going to be very useful to us today because it means that we can use t-tests like we saw yesterday to measure whether one of our coefficients is statistically significant. Okay, so here we've got just a kind of a way of visualizing the data. So this will be a little bit different than you've seen before, but say this is the x-axis, this is the y-axis, and say we've got data kind of here. What we have on this, what we usually call the z-axis, is how many of each values of y we see at each value of x. So that's why we have these like little distribution pictures right here. We're going to see normally distributed means that there are lots of values that are close to the line and there are fewer values that are further away from the line. That's all that means. That when we say that the errors are normally distributed, that's all that means. Let me pause for questions really quick. Just want to make sure that I don't get ahead of myself or the class. Cameron, Denelson, Derek, Esmeralda, Ibrahim, Kimberly. So yes, this is a 3D figure where we've got X and Y are the floor, and the third dimension is how common it is for us to see any value of Y at a value of X. Okay. So the sample means that we saw yesterday are normally distributed around the true mean. So remember, we were talking about we have sample mean X bar, it's distributed around some true population mean, and the sample means have a standard, have a variance of sigma squared. And so what we did is we would find the t statistic by converting whatever the population mean was into a standard normal. So we would take the population mean, we would subtract the true population mean, and we would divide it by the standard error of the population means. And what this value is it's a standard normal with a t distribution. And so all that means is that we can go to our t test table and we can calculate whether something is statistically significant or not. Regression coefficients are actually almost, they have kind of a very similar form. So first what we have is that our estimate is distributed with a mean. So if we kept taking new samples and re-estimating the beta, we would find that they are distributed with a mean of the true beta and a variance of the estimated beta. So that's what that is. And we can, just like we did with our sample means yesterday, we can do the same thing with our regression coefficients, whereby we basically subtract BJ from the true population mean and divide by the standard error of our estimates. And that number, quotient is distributed as a t with n minus k minus 1 degrees of freedom. And I'll tell you what that means in a second. But all this means that it's distributed t has a t distribution is that we can go to a t table and use the t table to figure out if something is statistically significant. So often what we'll be doing is we'll be proposing. Remember, we don't know what the true population mean is. What we'll be doing is basically we'll be proposing. I have a proposal, which we usually call a hypothesis, that the true beta is equal to some constant c. So I might say I think the true average height of American men is 5'10", and then I can take a sample, measure what we find in the sample, and then take the difference between my proposed population value and what we actually see in the data, divide by the standard error of the estimate, and that will be distributed as a t. And we can calculate whether our sample is consistent with a population mean of 5'10". So the t statistic is found by converting to standard normal. Beta, we just want to make sure we label everything. So this is the true population value. This is our estimate. From a sample. And this is the standard error of the coefficient, of the estimated coefficient. Okay. And then what is this? What does this mean? That T with n minus k minus 1 degrees of freedom. Well, what that means is that when you look at the table, I don't think I'm going to have you look at the table on the final or anything like that. Maybe for a homework, we'll do that. But that when you have n minus k minus 1 degrees of freedom, n is the number of observations in the data, k is the number of slope parameters, and 1 accounts for the intercept. So you'll have 1, basically k, if you could also think of it as all of the parameters in the regression would just include the constant. So you could have k include the constant as well. But for right here, we just have k being the number of slope parameters in your regression. Okay, questions. Does this feel natural? Does this feel like, oh, I've kind of seen something like this before? Or does it feel like, this is deep and I'm not sure I'm swimming right? Neb, Noah, Oscar, Saul, Stephanie, Warren, Yesenia. Okay, sounds good. So here we have regression coefficients. Here's a null. So usually when we have regression coefficients, the null hypothesis is that the coefficient is actually equal to 0. So this hypothesis states that the explanatory variable has basically no relationship or no effect on the outcome variable y. And we will reject, just one sec, yes, it's just a tweaked t-test. That's a very good way of thinking. It's this exact same thing that we were looking at yesterday, except it's for coefficients in a regression rather than sample means. I've gotten a sneak peek before and it seems familiar. Okay, good, perfect. We will either reject the null hypothesis at some level of confidence, typically 1% or 5% or 10%, which means that, for instance, if we reject it at 1% confidence level, it means actually that we're 99% confident that that the sample, that the true mean is different than 0. If it's at the 10% confidence level, it means we're only 90% sure that it's different than 0. We're not quite as confident. Or we will fail to reject. We don't reject. We will reject if B is very far away from, is sufficiently far from 0. So it's important to note that we never accept that Bj is actually equal to 0. There's not a thing where we're accepting that Bj is the same as 0. And why is that? Because we could always have a bigger and bigger sample in which it's not 0, but it's a very small value. So we never really accept that it is a 0. We're just saying we can't reject that it's 0 usually. Okay, so the null hypothesis is always that the beta is equal to 0. A one-sided test is usually that beta j is greater than 0 or less than 0. So if you know to begin with what the sign of the beta is, you would use a one-sided test, but we almost never use that. It means that, like, even if we got a negative beta j, we would be 100% confident that that's false. And we just never, that's not a very common practice in econometrics and statistics. I've just never seen anyone do that. The alternative hypothesis is that beta j is larger than 0. In this one-sided test, we will reject the null hypothesis only if beta j falls too far to the right of 0. And we have a completely analogous one-sided test where the hypothesis, the alternative hypothesis, is instead that beta J is less than 0. So the only reason that we use a one-sided test is if we're super sure that the beta is on one side and not the other of 0. Okay. So in a one-sided test, the confidence level is the probability of falling too far away from the constant. And in regressions, 0 is usually the constant. We're choosing a constant of 0, usually to test our regression coefficients. So basically, if we get a value, if we draw a value that generates a t-statistic over here, and we say that's really large, it's much larger than you would have expected if the actual regression, if the actual relationship was just 0. Okay, so suppose that we estimate the effective company profits and revenue on a CEO's salary for 60 companies. So what we're saying here is that the sample size is 60. And this is the regression. I think we've actually used this regression before. So CEO salary is 432,000 plus 0.258 times profits plus 0.021 times revenue. And then we've got some things that we haven't had before in our regressions. We have these numbers that are beneath each of the coefficients. And what these are the standard error of the estimate, of the estimated coefficient. So what we're going to do is we're going to test whether one of these coefficients is actually equal, consistent with no effect at all, basically with whether it's consistent with the beta actually being 1 in the population. So we're going to test the hypothesis that profits are not determined, do not determine CEO salaries versus an alternative that has a positive effect at the 5 and 10% level. So remember, our formula was really simple. We're going to have the estimated coefficient, beta j, on profits, minus, here what's our hypothesis is that it's actually equal to 0, divided by the standard error of the beta j. And so what that's going to be here is, on profits, here is our estimate, 0.258 minus 0, divided by 0.150. And so that's going to give us, I have it right down here, so I'm not doing this one in my head, but 1.72. And then that's going to be distributed as a t-statistic with 57 degrees of freedom. Why 57? Well, because we had 60, remember the degrees of freedom are n minus k minus 1. So that's going to be 60 minus k is 2, because we have 2 slope parameters, 1 on profits and 1 on revenue. And we have 1 constant here, so that's going to be our 1. That's why it's distributed as a t-statistic with 57 degrees of freedom. So let's look at our, maybe I have this open, maybe I don't. T. So we're going to look, sometimes they don't have the exact row you need, like we might not have 57 degrees of freedom exactly. So I'm going to look down here, I'm going to just round up to 60. So I'm going to look at this row that starts with 60 on the very left-hand corner, and I'm going to go across until we get to the 90% level. And at the 90% level, I'm just got to make sure I'm tracking. At the 90% level, we have 1.671. Sorry, I'm having a hard time keeping it big. And then at the 95% level, it's 2.0. So what we're going to do now is we're going to go back. So the critical value at the 95% confidence level is 2.0. And at the 90% confidence level, it's 1.0. 1.67. So let's go back 1.67. So we would find that this is, sorry. So here, let me turn to you. Is it the critical value at the 5% level is 2.0. The critical value at this one was 1.67. Okay. So is it, do we reject or not? Do we reject the null hypothesis at the 5% level? Yes or no? Can you guys fill in chat? Do we reject or not reject? And this is so important. I just think this, you're going to see this on the test. If this isn't clear, I really think it's just worth doing these examples right now, and we're kind of supervising together so that we can learn and so that we can make sure that we understand what's going on. Let me start up. Oh, I have. Do we reject or not? Okay, let me call on a few people. Yesenia, Warren, Stephanie, Saul, Oscar, Noah. Do we reject or not? Okay, so here we will not reject. Why are we not rejecting? Because our t-statistic is 1.72, and the critical value for the 5% confidence level is 2.0, which means that we don't reject the null at the 5% level. Okay, this is going to get like just too crowded so fast. So I'm going to clean this up a little bit. Okay. Do we reject or not reject the null? Okay, Leanna's right on track. But if you're not doing this at home, I really do think that this is going to shock and surprise you on the test. So I really encourage you to be thinking this through and trying to figure it out if you're present. Okay, so do we reject or not reject at the null hypothesis at the 10% level? And the answer is that we do reject at the 10% level because 1.72 is greater than 1.67, the critical value. This is the critical value. Okay. So it means that we have a 90% confidence that the t-statistic is not consistent with 0, but we're not 95% confident that it's inconsistent with 0. Does that make sense? It's big enough to be confident at a 10% level, but not a 5% level. Okay. So here's the null. Here's the two-sided null. The alternative hypothesis is that beta j is not equal to 0. So it could either be larger or smaller. In the two-sided test, we will reject the null hypothesis only if beta j falls too far to the right or of 0 or too far to the left. So usually we actually don't care whether the t-statistic is positive or negative. We're just using the absolute value of the t-statistic. It's important. So in a two-sided test, the confidence level is the probability of falling too far away from a constant, which in this case is 0 on either side. So what we're interested in is how likely it is that if we're getting a really large value, it's just far away from 0. So we're not constraining in the one-sided test. We're basically saying we know that the effect is positive. We're only testing for positive effects. In a two-sided test, we're just saying we don't know whether it's positive or negative. We want to test for either kind of effect. Okay. let's see. So now let's test the hypothesis that a firm's revenue is not a determinant of the CEO's salary versus the alternative that it does have an effect at the 5 and 1% level. So what are we going to do? Remember, we're going to take the estimate here, beta of revenue, minus 0, divided by the standard error of beta r hat. So what's that? We're going to take this coefficient right here, that's our estimate, 0.021 minus 0 divided by 0.005. And that is going to be 5 goes into 24 times, and 5 goes into 1.2 times. And again, that's going to be distributed as a T with 57 degrees of freedom because we had 60 firms and we have 2 slope parameters. So what we can do is go back to that table, and we're going to be looking to see what the, so we already know the critical value at 5%, if you remember, is 2.0. Let's go find the critical value for 1%. So at 1%, we're basically right here. We want to look at in this 99. And we're going to find that the critical value is this value right here, 2.704, because that's where the 99 column crosses the 60 row. So 22.66. I just want you to notice, even at the very end of this table, 3.2 is like the very most significant thing that you can get in the table. 4.2 is even bigger than that. So actually, I've already forgotten what 2.66. So this critical value is 2.66. So we're going to reject at the 5% level and also reject the null at the 1% level. Why? Because our t-value, our t-statistic, is greater than both the critical value for the 5% confidence level and the critical value for the 1% confidence level. Okay, let me stop there and take questions. Stephanie, Saul, Oscar, Noah, Ned, Manuel, Levi, Leanna. Okay. Awesome. So we're going to state, here are the steps. So when you see this in homework or on a test, maybe, so we will need the t-test table for all these problems, right? So I will go and look at and write a homework tonight for something about either the, I think we need some more stuff on omitted variables, so I might go work on that. But I don't think I'm going to make a test question where you have to look up on the table. I might give you a critical value, and you can tell me whether you reject or not the null hypothesis. So I'm going to try to make it more straightforward than you looking up on a table and that kind of thing. But yeah, if you you might take other classes where they do want you to take a use the table. So the first step is to state the null hypothesis. Okay. Awesome. Yeah, I think the homework assignment on omitted variables would be smart for yeah, I think it'd be a good practice. And then you're going to compute the t-statistic based on the null hypothesis. Then you'll find the critical values with n minus k minus 1 degrees of freedom. And then you'll reject the null if the t statistic is larger in magnitude. Oh, this is my sister in Norway. She's calling. Do you guys want to see her really quick? I don't think I can do it. We can do them both, can I? How does this work? Can you hear me? Oh, sorry. Can you hear me? Hey guys, I'm in the middle of class. Can I call you back? Will you be around in like 40 minutes? Okay, sorry about that. And if I don't get a chance to talk, okay, thanks. If I don't get a chance to talk to you again, can you please go find a book of children's stories in Norwegian? Awesome. Okay, I hope to talk to you in a little bit. Okay, love you. Thanks, hon. Sorry, she's in Norway, and I don't ever get to talk to her. So um, she's coming home this month though, so that'll be fun. I haven't seen her in about a year. Okay. Okay, so then find the critical value, reject the null if the t-stat is larger in magnitude than the critical t-value, and not reject if it's smaller. And the intuition is that we're constructing a standard normal distribution around the hypothesized value of the coefficient off, which is usually 0. If the estimated value of the coefficient is in the thin part of the tail of that distribution, then the value is probably not correct. The hypothesized value is probably not correct. Yes, she's on her mission in Norway. Anyway, it was weird because she was called to go to Norway, and then COVID happened. So she went to North Carolina for a while before Norway was accepting American expatriates. And then when Norway opened up again, she went to Norway. So anyway, and her Norwegian is apparently very good. So I'm kind of excited for her. She's awesome. I wish you guys could know her. She's just very funny and smart, which, I guess you would know that from knowing me. So so here we go. Let's do a little bit of thinking together. So in our example, profits appeared to have a much bigger effect on CEO salary, but they weren't statistically significant. So let's just go back and see that. So see here that the coefficient on profits is pretty big. It's 0.25, and the coefficient on revenues is 0.02. So the coefficient here is very big, but it's not statistically significant. And this coefficient is pretty small, but it is statistically significant. So why is that? Katrina, Cameron, Denelson, Derek, Esmeralda, Ibrahim. Katrina, what do you think? Hello, people in the void. Can you hear me?
Is the coefficient reflects how much changes between these variable to the salaries?
Yes. So how much those variables affect the salaries, that's right. The reason that the coefficient on revenue is so significant is because the standard errors are very small relative to the size of the coefficient. The standard errors on the coefficient for profits is really large. It's almost as large as the coefficient itself. So all that means is that we're not sure that this is any different than 0. Does that make sense, Liana? Okay. Okay, so let's write this out. What does that mean intuitively? It means we're actually not sure the larger coefficient is different than 0 because its standard errors are so large compared to the coefficient. Because basically what we're doing every time is we're comparing a coefficient to its standard error. If the coefficient is much larger than its standard error, then it's significant. If the coefficient is not much larger than its standard error, then it's not significant. When would we ever want to do a one-sided test rather than a two-sided test? The short answer is that you never want to do a one-sided test. The only time theoretically you do a one-sided test is if you know that the effect of some policy could only be positive, or the effect of some policy could only be negative, and that any other effect would be impossible. That's the only time that you do a one-sided test. So the practical answer is you never. You never. Okay. When would we ever want to test if a coefficient is equal to some value C that's not 0? So we could want to test whether a coefficient is equal to something that's not 0 if, for instance, there is another estimate of beta, and we want to test if our estimate is consistent with past estimates. Okay. Like I had this cool paper. Well, I think all my papers are kind of fun, but we used tax data from Florida. So we had every person that was working in Florida from 2003 to 2012. And we could see when they were changing jobs from for-profits to nonprofits. And so because it was tax data, we had millions and millions of people that we could study. And the only study that had been done before that used a couple hundred people in the current population surveys rotational group. So what we could do is we could compare our estimates to the estimates found in this other study, and we could rule out many 90% of the values implied by their confidence intervals. So they said, oh, well, the effect is 2, but that 2 has a standard error of like, 4 or something like that. So these huge standard errors. Our estimate was so precise, we could say most of their confidence interval we reject. So all but 10% of their confidence interval we were able to reject based on our estimate. So that's kind of an example of that. Okay, so confidence interval is a range in which we are confident that the true coefficient must fall within given the estimated coefficients. So the range is determined by 3 factors. First, it's the estimated coefficient, and that's the middle of the range. So if you think about the range, where's the middle? The middle is the coefficient that you're estimating. So if a coefficient moved, the range around it would move. The standard error of the estimate. So the standard error, we're basically going to take an estimate, and we're going to add twice the standard error and twice the standard error, subtract twice the standard error to get the range for instance, that would be for like the 95% confidence interval. And you need the critical t-values for our desired confidence level. So it's given by something like the following expression. So usually we're going to have the critical value in a large sample for 95 confidence interval is 1.96. So what we're going to do is we're going to take the lower bound is going to be our estimate minus 1.96 times the standard error of our beta. And then that's the lower bound of the interval. And then the higher bound is going to be beta j plus 1.96 times the standard error of our beta j. Okay. So that's going to be the 90, that will be the 95% confidence interval. Confidence interval. We sometimes write CI, confidence interval. It's not confidential informant. It's like a police show, it's a confidence interval. And so say we wanted a 90% confidence interval instead of a 95% confidence interval, we would just substitute out the critical value for 90% confidence instead of the critical value for a 95% confidence. So this would go down to something like, oops, can't remember what it was, but something like, 1.9, no, 1. There's something like 1.7 instead of 1.96. I can't remember precisely, but you would just sub in the critical value of the confidence level that you want for your band. And so what you're going to get intuitively is, say you want to be confident at the 99.999% level, you're going to need a bigger confidence interval to be very sure that it's within this 99.99999% likely to be within your thing. If you don't have to be very sure, it can be a narrower band intuitively. Okay. I am already starving. Oh, bother. Where did it go? Okay, I just got to go get some water and a snack. Can I show you? Let me see. I'm just going to put on my new favorite Chainsmokers song, and then I will be right back.
Dinner. It's more than just a meal you make every night. It's a chance to.
She has eluded your soldiers for 19 days.
She's public enemy #1 in Gilead. They're gonna find her. They're gonna kill her.
I ask for justice.
What happened? Oh, is it the end? Anyway, I like that one. My kids love that song. And they listen to, have any of you seen the new Addams Family cartoon movie? Anyway, there's a song in it that's kind of funny. It's like to the old Addams Family theme. But like the lyric is funny. It's like, you don't want to mess with me because if you mess with me, you're messing with my family, or something funny. So my kids sing that, and I just think it like cracks me up. Okay. Zoom meeting. Okay. Any questions here? Nothing? Okay. So what's the 95% confidence interval for the estimated effect of the company profits on CEO salary? Recall that there were 60 companies, including the regression. So that's how we get our degrees of freedom of 57. And we're going to find out what's the critical value at the 95% confidence level. And with 57 degrees of freedom, it's 2.00. So we're going to take the beta J, and we're going to subtract the crit value times the standard error, standard error of beta J. And that's going to give us the lower value of the range. And the upper value of the range is beta J plus the crit value times SE beta J. So all that's going to be is we're going to multiply 2 times 0.15, and we're going to subtract that from the coefficient, and we're going to add that to the coefficient. And those two values will give us the 95% confidence interval, the range of values that we're very confident the true population mean is actually within. So based on that calculation, we'll find that we're 95% sure that the true population beta J is between negative 0.047 and positive 0.558. So one thing that you can just notice right there is that obviously that crosses 0. So we can't be, we're not 95% sure that beta J is different than 0, because within the 95% confidence interval exists 0. Okay. So there's a 95% chance that it's within, that the true beta J is within that range. Okay, so this confidence interval, I'm just going to show it a slightly different way. Here we have our estimate was 0.258, and we had the upper end of the confidence interval was up here at 0.558. The lower level was down here, negative 0.042. And obviously that is going to include 0. So we can't reject that the true value is different than 0. Okay. So p-values are basically another way of thinking about the same problem. And the p-value, when we do an estimate, in Stata, it will give us a p-value, and all the p-value is the probability of obtaining a test statistic at least as extreme as the one that was computed, assuming that actually the null hypothesis is true. So say that the true effect were 0. What are the odds that we would get an estimate this large or this small, this far away from 0? So this is the precise percentage associated with the t-statistic rather than a generic range, less than 5%, for instance. So the p-value, as an example, let me just make it kind of more concrete. The p-value associated with a t-statistic of 2.3 is 2% using the t-statistic. So it means if we calculated a t-stat of 2.3, that implies that if we looked at the table, we'd find that there's a 2% chance of estimating a relationship that large if the true value were actually 0. Okay, So we can estimate the p-value using a t-table, but the Stata, it will make our life easy and it will give us the p-value automatically when we do work. So I'm not going to ask you to use Stata in the test or even on the homework, but I'll show you what that looks like when we use Stata. So here's our old regression that we're going back to. What's the p-value of the coefficient on profits? Remembering that there are 60 firms. So remember we had, to calculate the t-statistics, we subtract 0 from our estimate, and we divide that difference by the standard error of our beta hat, and that will generate a t-statistic of 1.72. What is our best guess of the p-value? Let's go to the table and just see what we got. So 1.72, 1.72. So I'm going to be here in this column that has a 60 on it. I'm going to be looking for something that looks like 1.72. So I'm guessing it's going to be something like, it's going to be something like the p-value will be a little bit greater than 10%. So let's see if that helps. Let's see if we're close. I think we get maybe something a little bigger. %. Okay, let's see if we get, so here we go. Oh no, this is totally not the same. So it's not gonna, I thought Stata was gonna check. I thought I had in here Stata check, but you might see it a little bit later. But all I did was I looked to the t statistic, that was closest to what critical value. And then I just looked where that critical value, what the confidence level was. And we found that 0.172 is very close to the crit value for 90% confidence. So I think that the p-value is going to be something like 10%. That's the probability that we would get a t-statistic of 1.72, even if the true coefficient on profits was actually 0. Okay. So I'll just show you what Stata does for us because it's nice. So say we have this data set. We're looking at the relationship between savings, outcome is savings, and the independent variables are income and age. And so we see that you have more savings as your income goes up, you save more money. And as your age goes up, your savings go down. So but it's not statistically significant, which we'll see here. So in this column is the t-statistics. So all this column does is takes t is equal to the coef divided by the standard error. Okay, so this is actually just dividing, for instance, 0.15 divided by 0.059 is equal to 2.61, etc. for the other rows. And then this is the p-value right here. This column is going to give us how likely are we to get a t-statistic that large if the true effect is actually 0. So normally, actually, I'm not looking at the t-statistic column, I'm looking at the p-value. And I'm looking usually for p-values that are very small. So this p-value is less than 0.05. So we'd say this is statistically significant. These aren't. These are you have a 55% chance of getting a coefficient that large, even if age doesn't matter at all. So we think, oh, that's actually pretty likely that age doesn't matter based on the coefficient and the standard error. But here we think, okay, income actually does seem to have a very robust effect. Okay, I'm not going to ask you about any of this on the test. I don't think if we do, I will prep you before before, but I don't think that we'll have anything like this. Okay. So yeah, that's just more data that we don't need right now. Okay. So this is an important thing. Okay. Sometimes people will say, such and such has a statistically significant effect on some outcome. And that sometimes doesn't matter. So you can have a statistically significant effect that actually doesn't matter in practice. So like, say that being out in the sun increases the probability of developing skin cancer by 0.00001 percentage points. And it was statistically significant. So you could have all these headlines that say, oh, it's a significant effect, a significant effect. But in practice, it's only a statistically significant effect. It only means that it's not zero. It doesn't mean that it's actually a large effect that's worth worrying about. So the statistical significance and the practical significance are sometimes very different. In the same way, you could have a big effect in a regression that's actually not statistically significant. And that doesn't mean that so for instance, say we found that, I'm trying to think of a good example, but say we found that, we have a small sample of heroin users and non-heroin users in the same high school. And the heroin users are doing, they have much higher mortality rate, but the difference isn't statistically significant, mostly because the sample is small. If someone came to you and said, well, the effect isn't statistically significant, you'd say, it might not matter. The effect is so large and the sample is so small that even though the effect isn't statistically significant, it could be having a major effect on children or on students. So this is just to kind of get in your head the fact that statistical significance sometimes makes things sound important when they're not necessarily important, and some things that aren't statistically significant are important. So statistical significance depends on the magnitude of beta and the standard errors. It's a statistical fact. It's not a fact about what's important in the world. And the statistical significance increases as you add data. As you increase the sample size, you tend to get more statistically significant things. Economic significance only relates to the magnitude of beta J. It's subjective assessment of whether it's important in determining or shaping Y. And things may be statistically insignificant only due to a small sample size. So this is just kind of to arm you into the world. I think that a lot of public institutions abuse statistics to manipulate and scare people in a way that's really disingenuous. Okay. So I am thinking, so these, I think that we're not going to do this. I just think we don't have time. These are called joint tests. So say you wanted to know whether beta 2 and beta 3 were significant at the same time, or that they offset each other, for instance, you can design tests for that as well. But I don't think that we're going to get into that today or tomorrow. Actually, I think that we'll just have to let that lie for the semester. Okay. So thank you for turning in your resumes. I enjoyed looking at them this morning. You guys are so impressive. I'm really excited to watch your futures. And I will go and try to design some homework for tomorrow. And yeah, I'll hang back and answer questions, but feel free to go and meet the rest of your day.